So a couple administrative items today, just very briefly. A reminder that problem set 6, which was distributed on Tuesday, will be due 1 week from today on October 27th. Also, we handed back midterms on Tuesday. If you weren't here for whatever reason, you should talk to Jeff, or are you in possession of the remaining midterms, Jeff? Okay, you should find Jeff in his office to retrieve that. Related, some of you last time had questions or issues with the grading, like things weren't added up correctly. Whatever the problem you perceive with your midterm grading, talk to Jeff or Elliot first. They did the grading. If it's a simple mistake, they'll simply fix it. If you have a deeper complaint, feel free to come to me, but talk to the GSIs first. Okay. All right, questions about administrative stuff? All right, let's get started. Okay, so I'm going to start today with another quote from Adam Smith. This is a very famous quote from an early section in The Wealth of Nations. The division of labor, however, so far as it can be introduced, occasions in every art a proportionable increase of the productive powers of labor. So I'd like you to pay particular attention to the last part of this. A proportionable increase in the productive powers of labor is being occasioned in Smith's story by increasing the division of labor. So bear that in mind. We're going to talk today about factory productivity. That'll be a bit of a review from last time. About marginal rates of technical substitution. That'll be newer material. Then we're going to talk about technological change, and with maybe an example toward the end. And that's, so I'd like to bear this quote in mind for when we get there. Okay. All right, so this really is a review. Last time we talked about returns to scale, but also returns to particular factors of production. And so we talked in particular about a production function, which might look something like this. It might be a function that depends on some input x1, some input x2. That could be capital and labor, for example, or some other inputs. And we said that the total physical product of good 1 was just was this function, varying x1, and I'm going to use this notation, holding x2 fixed. So if we vary x1, we can draw, this is total output y. We can draw some kind of function that might look like this. We'll call this thing the total physical product of good 1. Now, of course, there's another graph for the total physical product of good 2 that may or may not look anything like this. It might be quite different. It'll tell you how the total product changes as you increase x2, holding x1 constant. Okay. We also talked about the average physical product. That was the same thing as the average physical product of good 1 is equal just to the total physical product of good 1 divided by the quantity of the physical product that's being used. So the average physical product looks like this. It's the total physical product divided by the quantity of good x1 in this case. So total physical product in this picture, given some quantity x1, looks like this. So this is the total physical product. The average physical product looks like the slope of this line. This passes from the origin up to this point on the total physical product curve. And geometrically, you can see that the slope is just equal to the rise, which is the level of y we get, divided by the run, which is the total amount of x1 we're using. So the average physical product is just the slope of this ray. Yes? This is, yeah, so all these things are functions of x1 in this case, holding all the other inputs constant. I could change the notation maybe I do in the slides. So in the slides I'm using a notation that makes that dependence explicit. x1 condition on x2 is the notation I use there. I think I don't care deeply about how you write it. If it helps you to remember that this thing's a function of x1 holding other inputs fixed, feel free to write it this way. I also don't mind if you write it this way. We'll remember that that's a function. So we could be more complete, I suppose, by doing this. If you find that helpful, that's fine. Okay, so that's average physical product. And then finally, we had a third measure of factory productivity, the marginal physical product. And so the marginal physical product is just a partial derivative of the production function. So we have for this, MPP of 1 is just equal to the partial derivative of f with respect to x1. Okay, and geometrically, that's, of course, just the slope of this TPP function at the point x1. Yes, there's a question? Yes. It's not that it's equal to the slope of this line. Is that the question? Yeah. Okay, other questions about this? All right, so this is just jargon that helps us measure the consequences of increasing the amount of some input we supply to a production process on total output. There's sort of 3 commonly used ways to get at that. Okay, and that's all review from last time. So the next thing we talked about from last time was substitution. We wanted to get to the point of being able to talk about substitution between different inputs. And for that, it's going to be useful to talk about isoquants. So here's a picture of an isoquant for a production function. I'll write it up here. I'm not sure how clear that is. This is a Cobb-Douglas production function where output y is equal to x1, in this case raised to the 1/3, times x2 raised to the 2/3. Okay, so quick question, by the way. Does this production, can we say anything about the returns to scale of this particular production function? It's a Cobb-Douglas, Chris says it's a Cobb-Douglas. Okay, so it's a constant returns to scale production function. Why is that? Okay, so one way to do it is to notice that this is a special case of the Cobb-Douglas production function, which we'll write more generally as something like, I'll write it this way. Actually, I'll write quite a different one for you. So we have a bunch of inputs, 1 through n. The Cobb-Douglas case has some constant, which we usually denote a, times x1 raised to the alpha 1, times x2 raised to the alpha 2, and so on, all the way through xn raised to the alpha n. Or if you prefer this notation, it's equal to a product I equal 1 to n of xi alpha I. Okay, so what you can do is notice that this is a special case of this Cobb-Douglas production function, where a is equal to 1, where alpha 1 is equal to 1/3, and where alpha 2 is equal to 2/3. And then you can remember a fact, which we talked about last time. Here's the fact. If, for a Cobb-Douglas technology, we have the sum of all the alphas, I equal to 1 to n, equal to 1, then we have constant returns to scale. And similarly, we'll go ahead and note that if this sum is greater than 1, I'll ask the question, what does that mean? Increasing returns to scale. And that leaves exactly one case, of course, where the sum of the alphas is less than 1, and that implies decreasing returns to scale. Okay, so that's a nice, useful fact to remember. Notice something in passing here, which is that this issue about constant increasing or decreasing returns to scale doesn't depend at all on what the value of A is. A could be a large number or a small number, just scales things up and down proportionally, and so it doesn't affect the returns to scale of the technology. Okay. All right, so anyway, so that's a reminder about the returns to scale for Cobb-Douglas. Here are the isoquants for a Cobb-Douglas production function in this figure here. These should look familiar. They're a lot like indifference curves. In fact, mathematically, they're just like indifference curves for a Cobb-Douglas utility function. The important difference we've got here is just that we take the levels of output seriously. So at this bottom isoquant, output happens to be equal to 1, and it's measurable. We don't have to worry about intertemporal comparisons of interpersonal comparisons of utility, for example. A bushel of corn for one person is a bushel of corn for another person. Okay. All right, so that's that. I also showed you, I brought along a model last time that I didn't bring today, but here's a picture of it. This is the Bressler corn production function. Notice that this one is not a Cobb-Douglas production function at all. It's a quadratic production function instead. It's a second-order polynomial. It's got multiple inputs. In this case, the inputs are supposed to be water and fertilizer. Does this production function exhibit? What can you say about returns to scale for this one? None of you are saying anything, which is kind of wise. That's not a very well-posed question here. You know, if you imagine starting, say from here, where the inputs are, I guess, I don't know, something like 1, 1, and increasing all the inputs, you get a rate of increase which is less than 1 for 1. That's fine. And eventually it becomes negative. If you start at a different point, though, you might have a higher rate of return as you increase stuff. So the question is, this function doesn't have sort of globally constant returns to scale or globally constant decreasing returns to scale or anything like that, because it goes up steeply and goes down on the other side. It's not a homogeneous function. It's another way of saying that in the way that the Cobb-Douglas production function is. All right. The thing to note here about the isoquants, that's what I really want to point out, is that here they're displayed more or less in the input part of the graph here. So here we have, I guess, x1 and x2, and I hope you can see these isoquants sort of in the bottom of this figure. Okay. If we take that bottom piece and sort of lift it up and lever it around to the front of the screen, we get something that looks like this. So this is just the base of that figure you saw a moment ago, where again we have water on this axis and fertilizer on this axis. So these are just pictures of isoquants. Is the construction here clear? All right, so now what I want to do is, you guys understand what isoquants are, it's only by analogy because they're a lot like indifference curves. So now what I want to do is think about something which is analogous to marginal rates of substitution, and that's the marginal rate of technical substitution. So you'll recall that one way of thinking about the marginal rate of substitution in the demand case was that it's equal to the slope of an indifference curve. On the production side, we have something completely similar. We have the marginal rate of technical substitution. At a point, it's going to be equal to the slope of the isoquant. So I've given you a picture here with the same production function. I just picked out the particular isoquant that yields a total output of 4 units. And at this particular point, there's a slope, I guess it's a little bit more than 1. And this is cut off. That should read MRTS. So the marginal rate of technical substitution is just equal to the slope of the isoquant at a point. Okay, so for the particular production function I've drawn here, you can see that it's decreasing as we vary x1. So if we imagine starting off with a very low level of x1, but being on this isoquant someplace, the interpretation is that we have a very small amount of that input. So maybe x1 is labor and x2 is capital. So imagine starting off at a point up, like way up here, but there's a small amount of labor and a large amount of capital. What the slope of this isoquant tells us, well, I'll ask you, what does the slope of the isoquant tell us up here, where it's quite steep in absolute value? So we start off production using a lot of capital and a little bit of labor. Yes? So. How much x2 is necessary to replace change in x1? That's what the slope tells us. What does the fact that the slope is steep tell us? Back here where the slope is steep. What particular things does that tell us about the marginal? Yeah, Eric. Yeah, in a way. I mean, we have to take into account the price of the labor and the price of the capital, but that's right. A small amount of additional labor is going to buy you a larger increase in output than a small amount of additional capital. That's the way to interpret that. It's useful to contrast this with the previous isoquant here. Suppose we're up on, let's take this isoquant here. Suppose we're up at a point like this. What's the marginal rate of technical substitution here telling us? Can you guys see that point? Yeah, Eric. Yeah, okay, so I guess 2 things. First of all, Eric's noting something we pointed out last time, which is that here, where the isoquant is positively sloped, it's telling us that we can grow more corn in this case by reducing the amount of this input. And so we can stay on exactly the same isoquant by, picking a point like this. It has the same amount of water, I guess about 10 acre-feet or something, but much less fertilizer. So you can observe that graphically because this point on the indifference curve lies directly above this. On the isoquant lies directly above this point on the isoquant. But we can also just observe it sort of locally by noticing that we have a positive slope at that point. So we basically never had positive values for the marginal rate of substitution. The slope of the indifference curve when we talk about demand. Here we can because we don't have something analogous to the axiom of non-satiation. So we can get the sign that the marginal rate of technical substitution is different at this point than it is down here, and giving us a message that we do well to substitute away from good x2 in this case. Okay. All right. All right. So I want to do something which is very similar again to something I did when we talked about utility, and that's to derive. We talked graphically about what the marginal rate of technical substitution is. We said it's the slope of the isoquant. Let me go ahead and derive an algebraic expression for you. So here's our picture. I'll have inputs x1 and x2, some kind of isoquant like this. And we said graphically that if we pick out a point here, the slope of this is the marginal rate of technical substitution. Okay, that's fine. Now, here's how I want to think about this. I want to remember that this is all coming off a production function, which I'm going to call f. Depends on inputs x1 and x2. And what I'm going to do now is think about what happens if there's a small change in the inputs. So I'm going to take the total derivative of this expression. That's going to give me... I'm sorry, what's it? y is it's neither. So this is the production function. So y is the amount of output you get, like bushels of corn, and the x's are inputs like water and fertilizer, in that example. So I'm going to take the total derivative of this thing. That'll give me an expression that tells me something in terms of the marginal physical product of these goods. So this expression, of course, is the marginal physical product of x1. This will be times the total change in x1, plus the marginal physical product of good 2, which is this partial derivative, times the total change in good 2. Yeah. Okay, so does this look familiar? I'm just taking the total derivative of y. This tells me how much y increases if I change x a little bit, x1 a little bit, and change x2 a little bit. Okay, and now to answer the question about getting an expression for the MRTS, what I want to do is go ahead and remember something important about isoquants. Any thoughts about what that important thing might be? Yeah, it's that along an isoquant, output is constant. So this is, in my earlier slide, I had y equal to 4. The point is the y doesn't change as we move along the isoquant. That's what defines the isoquant. So as I move along the isoquant, this total change, dy, has to be equal to 0. And so from that, I can just do a couple little algebra steps. I can move dx2 to the other side here. So I'll have df dx1 equal to minus df dx2 dx2. And then I'm just going to divide. Let me do this, actually. Let me divide through by dx1 and by dx2. That's going to give me the result that minus dx2 divided by dx1 is equal to df dx1 divided by df dx2. Or, if you prefer, it's equal to the ratio of the marginal physical product of good 1 divided by the marginal physical product of good 2. And this is what we're going to define to be the marginal rate of technical substitution. Okay, so this is exactly analogous to substantive utility functions. So the marginal rate of technical substitution is equal to this ratio of marginal physical products. It's equal to minus the slope of the isoquant, and that's the marginal rate of technical substitution. Okay, questions about that? You all seem strangely subdued today. Yes, sorry. So I was taking the. I just wanted to point out that it was constant. In the example I had here, I had y equal to 4, so I was imagining. So along this isoquant, I had total output constant at 4. That's what defined this isoquant. And I was just doing this by analogy. Output's always constant, a constant like than before. Yeah. Okay. Other questions? Okay. Okay, so that's the marginal rate of technical substitution. I want to talk now, switch gears, and talk about technological change. And so I have a couple things to say about that. A production function, when we think about these production functions, it gives us a mapping between inputs like labor and capital, or like water and fertilizer, and total output. Let's take a corn example for a moment. There may be different ways to use water and fertilizer to produce corn, or to combine labor and capital to produce some kind of manufactured good. And so if there's just a difference in process or technique that distinguishes different ways of producing a good, we'll describe those as being different technologies. There may be different production functions as well, but we'll call them different technologies. Okay. So there's a very common example of a production function that economists use to describe this thing is a Cobb-Douglas production function. And we can think about, I'm going to use the same one I defined a moment ago. Is it still here? Yeah. So we defined this Cobb-Douglas production function before. We have, of course, output y. We have inputs x1 through xn. There's also this parameter a that I mentioned in passing. We'll often call this something like a technological parameter, or sometimes just a technology. And so that's imagining varying a is one way of imagining changes in the technology that people are using to produce a good. And you can see right here, it's quite clear. Larger positive values of a mean larger values of output, proportionally higher quantities of output. So a better technology, in this Cobb-Douglas case, is a technology that has a larger a. Okay, there's some other parameters here too, or some of the names for the a's first of all. Sometimes it's called the total factory productivity parameter, and you can sort of see why. I'll show you something else in a moment too, but you can sort of see why. If you increase a, it increases the productivity of all the other factors of production. So that's the total factory productivity, sometimes called technology, as I said. There's also a tradition of using these Cobb-Douglas production functions in macroeconomics to model things like a country's GDP. In that setting, these things are often called a Solow residual, named after famous macroeconomist Robert Solow. Okay, so there's names for these other parameters as well in the Cobb-Douglas setting. So a we'll call the Solow residual or technology or something like that, TFP. These alphas have names too. In the case I have up here, I've got labor and capital. The alpha in this case, the exponent here, is called labor's share. And the reason for that, we'll come back and show this, is because a firm that's operating this technology will have some input costs. It'll be paying for labor and capital. And it turns out that if alpha plus beta sum to 1, we have a constant returns to scale production function, it'll turn out that the total proportion of their costs that they'll spend on labor are going to turn out to be equal to alpha. So similarly, beta will be called capital share. If this is a constant returns to scale production function, so alpha plus beta are equal to 1, the total expenditures of the firm on capital, or capital services, will be equal to beta. Okay. All right, so that's some jargon for you. And here's